Let's talk a little bit about non-destructive testing. I should have had another hour to talk about this, but I've told too many stories or whatever, but that's okay. Just forces me to condense things a little bit. There is a difference between NDT and NDE. Anybody know the difference? Besides, one has a T in it, one has an E. NDT stands for what? Non-destructive testing. NDE stands for non-destructive evaluation. So which one is the subset of the other? NDT is a subset of NDE. NDE actually requires intellectual input. Okay? NDT is done by some technician who would rather go home early. Okay? And there are various books. Most of what I'm going to talk about comes out of this book by ASM International called Non-Destructive Testing, which is a good summary. However, this is an even better summary. It just came out this year. I just got this about 2 weeks ago with a non-destructive evaluation. So this actually discusses the techniques of making the measurements. This actually is written by some of the top people in the field. It's edited by one person, but this is a much more scientific version that I haven't had a chance to really look at very much yet. But in any case, in non-destructive, he calls this non-destructive testing, but in fact it's non-destructive evaluation. We don't call them flaws, we don't call them defects, we call them indications. There's something that showed up on the detector. We don't know what it is, and that's the great mystery, and that's what all the engineers will debate, okay? And now the evaluation means that you have to interpret what that indication is. I mean, let's say I've got a situation of, we talked about ultrasonics before. If I yank out this thing on ultrasonics, in ultrasonics, I'm sending some sound waves down, and if they hit the back end of it, I get a peak here. This is the initial peak of the sound, and the echo comes back at a long time. This is time axis here. This is intensity of the sound versus time. If there's a flaw in between, at a defect, I'll get an echo from the defect at a shorter time in between. So let's say I get one of these things. On the oscilloscope screen, that's just an indication. It's not a defect on the oscilloscope screen. I mean, a defect on the oscilloscope screen might be a scratch or you know, piece of tape or something like that. But in the material, it's just some sort of indication. And the wonderful thing about most types of non-destructive testing is there are multiple reasons. I remember once pipeline company, they send pigs, what they call pigs, down the pipeline every 5 to 10 years. A pig is nothing more than a little conveyor that you put in the pipeline, and the fluid going through the pipeline carries this thing down through the pipeline, and the little conveyor has got all kinds of non-destructive test equipment on it, typically eddy current type of detectors. And it has a big recorder on it, and it will record the data for the next 10 miles or 20 miles or whatever, as the fluid, whether it's gas or liquid, is pushing this thing through the pipeline. And they call these things pigs. So you pig the pipeline, and you get indications, and you get, you know, in 20 miles, you record lots of data. And you then have someone who doesn't have anything better to do, and they sit there and they look at wherever there's a little blip. And you compare the blips from the last time you did it 10 years ago to the blips you have today. And if you get a new blip, you say, ah, we have an indication. I remember once going down to Texas because they had found a blip. And this was in a river crossing, it just so happened, which makes things a little more difficult. It wasn't as if you can just dig up the ground and go down there and see it. You had to actually, you were going to have to go underwater and dig up the pipe underwater and try to see it. So this was going to get pricey to have divers get in there. So I went down there to tell them what this indication might be. And I came up with 10 different possibilities, of which 8 were innocuous and 2 were significant. And the ultimate conclusion is, well, you're probably going to have to spend the money to go down and see if it's significant. Anyway, because there are, you know, because the indication doesn't tell you everything about it, okay? So you've got this indication which you have to interpret, and it can be a false indication, really, not a false interpretation. I guess I probably shouldn't be using this guy's thing. You can have a false indication, which is, just extraneous because of something else, or one that's non-relevant, but you can also have a relevant one, okay? So I found 8 non-relevant causes, or false causes, and there was really nothing there, and for some other reason, just the transducer lifted off the surface or something. But the relevant ones, if you have relevant indications, you have to do the evaluation. And the evaluation requires some engineering judgment as to accept or reject. Okay? Well, whether you're going to accept or reject depends on the material and the size of the flaw. And if we go back to our fracture mechanics, the strength of a structure is not related to the stress. It's equal to the stress intensity, which is equal to the stress times the square root of pi times the crack length, or the flaw size. So I really need, if I really want, in the old days, going up to World War II, 1950, we thought the strength of the structure was related to the stress capability of the material. After we ran into the fracture toughness problem on Liberty ships, we realized the stress intensity. I mean, this was all worked out in 1925, but it wasn't really, didn't hit home until after World War II, around 1950s, that we really are interested in the stress intensity, not the stress. And the stress intensity is a part of 2 things. The stress, which we calculate very well now. I mean, we got finite element programs that will calculate this pretty accurately to a couple of percent, within a couple of percent. However, the flaw size, what's the flaw size, and population and distribution? And we still can make, us consultants can still make lots of money arguing with people over this. Let's take a metal and just put some typical numbers in. A typical number for steel or aluminum, even some titanium alloys, might be 50 ksi square root of inch for K. You might stress it at 25 ksi, and you put pi c in here, and you find that C, the critical size flaw, is 1.3 inches. Okay, that's a pretty good size flaw. If it's a surface flaw, it's 1.3 inches. If it's an internal defect, it's 2.6 inches. Double, okay? So, hey, even I could find that one, okay? Now, if it's a ceramic, a typical fracture toughness might be a good ceramic. The ones they call the tough ceramics might be 2 ksi square root of inch. If I were to stress that at 20 ksi, pi c, you put that in, and the critical flaw size is 3/1000ths of an inch, about the size of a human hair. Okay? Now you know why I consider ceramics to be non-structural materials, in spite of what the ceramists say. I consider the term structural ceramics to be an oxymoron. Okay? There is no such thing as a structural ceramic. They're only the ones that are about to break. So you don't stress things very high. In fact, typical stress on reinforced concrete, anybody know what it is? 5 ksi. But then you have to, that's because the rebar inside, okay? You have the steel bars inside. Okay, you would never build something without the steel in it, intentionally anyway. So anyway, we've got to know something about this flaw size population. Now, there are techniques. In fact, I got in a big argument. What was it? I can't remember what I think it was a helicopter crash. But in any case, got in a big argument with another expert. And he claimed that by ultrasonics, he found a reference that said you could find flaws with ultrasonics as small as 1/1000th of an inch. That's absolutely true. Under absolutely ideal laboratory conditions, you can find flaws. If you know they're there, you can find them. They're 1/1000th of an inch in size. I mean, you can get a signal that you'll find a blip, okay? But if you go and do a study of what people find in the real world, the smallest flaw that people typically find with any reliability is about 1/16th of an inch. A lot of times, maybe you should only be saying a 1/10th of an inch. And what reliability? In fact, I didn't make an overhead of it, but the curve for probability of detection versus flaw size, if this is a 1/16 of an inch, the curve kind of goes up like this, okay? And there's your 1/16 of an inch, so to have a reasonable probability. Now, the interesting thing is the probability of finding it is about 1/2. And I don't care if it's a 3/8 inch flaw. The probability, because you got human error here, it has to be interpreted by someone who's earning slightly more than minimum wage and gets to look at these things day in and day out. Okay? It's no different than the X-ray scanners at the airport. Okay? I told you the story about how they have now made it into a video game. Didn't I tell you that story? This was before September 11th, and I serve on the National Materials Advisory Board, and they do research evaluations for the FAA on where the FAA should put their money. And so we got presentation 2 years ago from the head of security for the FAA. This is before September 11th, and a lot of his information is classified, and we weren't in classified things, so he couldn't tell us everything. But he gave us about a 2-hour presentation. And one of the problems is, before September 11th, the probability of finding of an employee there actually seeing a knife or a gun or some weapon was 1 in 250,000 images. Now, if the probability of actually finding one is 1 in 250,000, which might be several years worth of looking, I would think, at these things, people would tend just naturally to quit looking for them because they're unsuccessful. So he was very pleased. This was 2 years ago. The government was putting in the first 50 units around airports where they had done an algorithm on the digital image so that they could put a fake knife or a fake handgun in someone's bag, like 1 out of every 75 times on average. So now this becomes a video game to get the worker to want to look for them and kind of reward the worker for finding it, okay? And then if he find it, he would hit a button and it would say, this was just a test, congratulations, you got this one, you know? And they would find out what the reliability, they'd be able to monitor the reliability of these people looking at the images. And if it was one of those 250,000 times where it really was a weapon, it would say, oh, this is not a test, take appropriate action, which means run, I guess. But in any case, you know, so you can see the human error in the detection at the airport is really no different than the human error in non-destructive testing. And there's a lot of Hawthorne Effect. Anybody know what the Hawthorne Effect is? Hawthorne Effect is named after a professor at Harvard Business School back in the 20s who was studying workers in textile mills and looking at their efficiency, kind of time and motion type studies and things. And he found that the ones he evaluated were much more productive than the ones that he wasn't watching. And that was because they were impressed to have this person in a suit standing over them, asking them what they're doing and stuff, and so they started doing a better job. And so this professor's name is Hawthorne, so they named it the Hawthorne Effect. When people discover something, they start paying more attention to it. Back 20 years ago, there was a pipeline being built in Australia. And for whatever reason, some of the pipe was made by an Australian company, some of the pipe was made by a Japanese company. The Japanese pipe was actually looked better, the welds looked better and stuff. But the Australian pipe got a bad rep among the people reading the x-rays. And they had like 10 times the reject rate on the Australian pipe as they did on the welds on the Japanese pipe. And this got to be a multi-million-dollar thing. Who's going to pay for all these extra repairs on the Australian pipe? And what is it in the Australian pipe that makes it more difficult to weld? Well, what they finally learned is when they went back and did a blind study of the x-ray film, there was no difference between the Australian and the Japanese pipes in terms of weld defects. It had nothing to do with the steel. It had to do with the fact that the weld inspectors didn't like, when they saw it came from an Australian pipe, they decided that they would reject those if they saw any indication. Whereas the Japanese, well, that's the good steel. We don't have, that's not really a defect, that's something else, right? So, I mean, the Hawthorne effect is when people start paying more attention to something, you start seeing more rejects or something because, oh, you're expecting to have a flaw, or you're not expecting to have a flaw, you have fewer rejects. So there's all kinds of human error. This thing is pretty flat, and it only goes up to 50% detection. So what does that tell you? Well, it should tell you that for most types of non-destructive testing, or non-destructive testing, you're only doing it as a quality control tool to try to make sure they're not producing really big defects. I mean, let's face it, if I were to put in typical numbers for HY100 and stress levels and stuff, I'd still end up with critical flaw sizes that are on the order of a couple of inches, okay? But I'm looking for flaws that are 1/8 of an inch in size. And if you go to most of the welding codes, the structural welding code or the ASME boiler and pressure vessel code, they're looking for 1/8 inch defects. Why? Because they know that they can, if they throw a sample or 10 samples at 5 different inspectors, the odds are a number of those inspectors will find the 1/8 inch flaws. About half of them will find the 1/8 inch and bigger flaws. So you have a reasonable reliability, but it's only about a 50% reliability of finding it. That's the important thing to remember. If you now assume that your structure has no flaws bigger than 1/8 of an inch, you're kidding yourself. Okay? But as long as I don't have too many flaws of 1/8 of an inch, I'm dealing with the fact that I know that things are going to be Gaussian distribution. Okay? If I only have a few flaws that are 1/8 of an inch, how many really big flaws am I going to have? None. Okay? Essentially. If instead the population of 1/8 inch flaws is down here, I could have some big flaws that could be critical to the structure. So all I'm doing is trying to weed out whether my distribution is, the center of my distribution is here or here. Okay? I'm going to have other flaws that didn't get seen. And you have to recognize that. Most people don't recognize that. Most engineers think, well, I inspected it, and if they didn't find it, it must not be there. Yeah. Okay? Good. I'm glad you think that. So, in any case, so that's the first thing to know about non-destructive testing, is its reliability is not what most people think it is. But it still serves a very important purpose, but you usually set things much tighter than you can really, than you can actually tolerate. And that's a good thing. Well, before I start that one, let's look at inspection requirements. What I'm going to do, if I go to different types of codes and standards, let's say I've got a pressure vessel, and a pressure vessel can be a pretty critical thing. I was down in Connecticut yesterday looking at a storage cylinder for some chemicals that blew up at 500 psi and great big fireball, and 2 people burned fairly seriously. Not a lot of property damage, but basically the pressure vessel. Now, this particular pressure vessel just didn't have a pressure relief device on it, and it only stood about 5 feet high and 30 inches in diameter. So I think there's a problem there. But nonetheless, pressure vessels tend to be critical because when they blow, they do a lot of damage. So it's critical, and typically the requirements would be 100% visual inspection of the welds plus 100% radiographic. Now there are different levels within the boiler pressure vessel code, but I'm just kind of giving you a typical. For a critical structure where a flaw can cause a catastrophe, you're going to do, and whether it's radiographic, you can also substitute ultrasonic testing or something else, okay? Magnetic particle or whatever. If I'm talking about machinery or a bridge, I might do 100% visual and 10% radiography. Why? You're trying to reduce the cost, but the consequences of failure are nowhere near as big. Bridges are redundant structures. I lose one beam in a bridge. It's usually a redundant structure. I mean, anybody been to New York and you come over to George Washington Bridge, and as you get into Manhattan, there's these 20-story apartment buildings, okay? 15 years ago, they called me in, and they had a 9-foot crack in a 9-foot beam. The Port Authority had been knocking some concrete off, had this 2,000 foot-pound hammer to knock off the concrete, and they just happened to hit the steel. They claimed they didn't, but I found the gouges in the steel. Okay, how do you get a half-inch deep gouge in a piece of steel unless you hit it with that big hammer? Okay, and there was a crack running right from that thing. Steel was more brittle than it should have been, but anyway, nonetheless, the building didn't fall down. There were a whole series of these beams underneath. Okay, now they shorted up, and for a year, you couldn't use that lane of traffic on the approach and stuff. The more interesting thing, I remember when I was first called in, I got this call from someone. He said, he was a building owner, says, we want you to come to New York, and told me the address. I didn't know New York, so I get a cab from LaGuardia, and he drops me off. This does not look like the nicest area of town. Okay, and in fact, I saw these little empty capsules on the sidewalk. And here I am with my $3,000 worth of camera equipment over my shoulder, right? And I looked around for the cab, and he's gone. And I look, and this is the address. And I go up, and the place just, graffiti all over the walls and stuff. And I go, and here's this solid steel door with these heavy hinges and like 6 or 7 deadbolts on it. And I knock on the door, and I hear this person shifting with the deadbolts, and I'm looking behind me the whole time, make sure I'm not jumped. And this guy opens up, and here's this Hasidic Jew wearing his, forelocks and his black hat and everything. Oh, welcome, welcome. You're also Atzvan. Okay, this apartment complex is owned by these very religious Jews. And you also have 7 children, and I have 7 children. We got along wonderful, okay? And then he takes me down to show me the beam, and he's banging the pipes as we go. I said, what are you doing that for? He says, just to scare away the rats. Anyway, I get down there and said, yep, that's a crack. It's 9 feet long and a 9-foot beam. Then he told me the story about when they had the tenants meeting with the owners to tell them that they had this problem of a crack in the basement. All the tenants wanted to go down there afterwards and get some of that crack. Okay. Anyway, but it's redundant structure. It doesn't fall down. If you have a failure in the weld of a pressure vessel, well, one failure and the whole vessel goes, right? One failure here, okay, you got to repair it. Well, there's nothing catastrophic. Usually on a piece of machinery, hopefully no one gets hurt. The machine stops, you fix the machine, and you usually don't destroy the machine, okay? But even if you destroy the machine, it's not as if you blow up the whole city block or you blow up the whole factory, right? You just have to repair the machine. So a lot of this is, there's a judgment, engineering judgment goes into what is the consequence of failure. For years, I've worked with the division of Johnson & Johnson, makes medical instruments. And back in the 80s, they used to use me all the time with their quality control people, and they'd say, we found this flaw in our manufacturing process. Do we have to scrap all 500 parts worth $500,000 or whatever, or can we ship them? And they were letting me put my house on the line by writing a letter that would go into the, would be there if the FDA ever had a problem. And I'd say, well, okay, well, what is this used for? And if it fails, what will happen? Is someone going to die? I mean, if there's a hydrocephalic shunt and it fails, it's embedded in your brain and it fails, and you die, hey, you can scrap it. It's okay with me. Okay, well, not my $500,000. Okay, but if it's a scratch and it's just a cosmetic thing on a pair of scissors or something, well, okay, it's not going to hurt anybody. Okay. So there's a judgment that goes into all these things about what are the consequences of failure. And I found that they were just using me because no one down there wanted to take the heat if someone was wrong. They let me take the heat. What about a joist? Okay, a joist being, if you, well, not in here, this is a concrete building, but if you go to a shopping mall and you were to peel away the false ceiling, you would see these steel bar joists up there. Basically are the beams that are holding up the roof. I will tell you that inspection is 100% visual and nothing else on those welds. I also tell you that the average welder has 2 seconds to make both those welds, or to make those welds per weld, and he's supposed to do the visual inspection himself. Okay? How good a visual inspection do you think that is? Also, I will tell you that the Steel Joist Institute welding code is the the least stringent, how about that? The least stringent code I've ever seen. They will accept virtually anything. Okay, but the roofs don't come down that often, and usually there's enough creaking and groaning under the snow load, that's usually what brings them down, that people get out. I've actually never heard of anyone being hurt with the roof actually falling on someone, because you know, if you know you got 3 feet of snow on the roof and you've had a lot of snow and you start hearing this creaking and groaning for a few hours, they tend to clear out the area and try to shore it up. So I mean, does it work? No, they're really doing no inspection there, in my opinion. But you know, it really doesn't cause failures. It causes failures, which might be property damage, but there's no hazard to people. So there are different levels, and those levels of inspection depend on the criticality of the failure.
When you look at areas like Florida and Hawaii, which have the hurricane-rated houses,
yep.
What exactly do they do to make reinforce a 150-mile-an-hour wind or whatever?
Well, the two big loads on buildings, well, where it's snow loads are usually the big load, but beyond that, wind loads are usually the big loads, and they just the wind loads are actually usually more significant than just the static structure loads by a factor of 2 or 3. If you're in the hurricane region, it might be 5 or 6 safety factor, so that you have to put on there to allow for the wind suction. Because I mean, think of it, as the thing goes over there, it's kind of like an airfoil type of, and you get suction, and you actually get lifting of the roof, okay, from the suction of the airfoil. And you can, it's well known. You go to the codes, and the codes will tell you actually for snow loads and for wind loads, they'll have a map of the United States, and they'll have little ISO plots that tell you that if you're in this region, you can expect 24 inches of snow on the roof. If you're here, you can expect 110-mile-an-hour maximum winds. Okay, I think the World Trade Center was designed for 150-mile-an-hour winds. Okay, and the wind load was the dominant load on those buildings. Okay. So it's just, you just build a bigger safety factor if you have heavier winds. And then when you have the 1,000-year storm with 200-mile-an-hour winds, you lose your building. And that's what happened in Hurricane Andrew. They didn't have stringent enough codes for people's houses and stuff. And Andrew came by at 150 miles an hour, and they designed them for 100 miles an hour, and guess what? They were stupid to design in Florida for 100 miles an hour. Okay? But, I mean, we let people build their homes in floodplains, and then the federal government provides them with flood insurance, right? I mean, you know, I grew up in Virginia Beach, and you know, people build their home right on the ocean, and they know that the ocean is eroding away the beach. In California, they let them build on the hillsides that they know are sloping down from the rains and the sludge. And you know what? When they lose their houses, oh, it's terrible how these people have lost their home. They were idiots to build it there to begin with, and I got to pay for it as a taxpayer. Sure, I think they should give them a tent and tell them to start again. Anyway, it's not that I'm heartless. They're rebuilding their homes with my money. Anyway, but it's not politically acceptable to make people responsible for doing stupid things. Anyway, okay, let's see how much time I'm going to have here. If I want to do non-destructive testing, I'm going to have to find these flaws that we were talking about. I have to have energy interact with matter in some way. And so I can start on the highest level of abstraction here. I can have electromagnetic energy, which is all the way from radio waves to X-rays with light in between. I can have mechanical, which is acoustic emission or ultrasonics where I'm vibrating it. I can have thermal energy. A lot of times on composites, if I want to see if there's a flaw, I use the poor thermal conductivity of the polymers, and I heat up the composite on the backside, and I use a thermal imager on the front side, which is an electromagnetic detector, and I see if it comes through, if the heat comes through uniformly. If there's a void there or a lamination, that's a thermal barrier, and I won't see uniform heat coming through if I heat it uniformly on the backside, for example. Okay, so that's one way to use thermal energy. I can use particles, which could be neutrons, or electrons, or protons, and I can hit it with those. For example, I want to know the composition of some material, and I just happen to have a nuclear reactor, and the material I can put in the nuclear reactor, and I hit it with neutrons. I can change that with the right energy neutrons. I can change that isotope to an isotope that's radioactive that'll have a characteristic decay time. I can measure that decay time, and I've now done what's called neutron activation analysis. So I'm looking for, I used to do this for my oxygen in my titanium welds. I'd send it up to Toronto because they charged me 20 bucks a sample. Anywhere around here, they cost me $250 a sample. But the university up there, it's all government subsidized. Well, might as well use some Canadian tax money to subsidize U.S. government research, right? And they were happy to get the 20 bucks a sample. But basically, they put it in the reactor, bombard my weld with neutrons. The oxygen would go from what, oxygen 16 to oxygen 17 or 18, whatever it was. They watched the decay of the oxygen 17 and 18, and they'd be able to tell me within a few parts per million. Very, very accurate analysis. So they're using particles to do the testing there. Positrons, okay, the great new imaging technologies of the brain. They basically produce these short-lived isotopes, convert it to something that you can drink or breathe, like oxygen, okay, to breathe, and it goes in, it reacts, and it releases positrons, and so they actually you breathe some of this gas, and these are isotopes that have a half-life of like a half an hour, and they actually can see what's happening in your brain by imaging the positrons coming out of your brain from these radioactive gases that have a very short half-life, and they can see, you know, they then give you a milkshake and see which part of the brain gets stimulated by milkshake, right? Or something. So that's a form of energy. If you want to look at what people have used, if you just take the electromagnetic spectrum, which in the electromagnetic spectrum I've got radio waves, I've got microwaves. In microwaves I use nuclear magnetic resonance, which we now call MRI, because people are afraid of nuclear energy, even though nuclear magnetic resonance has nothing to do with nuclear energy. So in here, infrared, we have thermal imaging from the infrared radiation. We have visible, looking at something. You have ultraviolet, X-ray. You have gamma ray out here. Virtually all of those, anything you can think of on the spectrum, someone has used for non-destructive testing. Okay? Ooh, look at that magic. Magnetic resonance imaging. Okay, basically you go into this little chamber where there's hardly room to sit. I had it once when I had cancer. And I'll never do it again unless they put me out. I don't like small spaces. But basically they hit you with a bunch of radio waves, and then they look at a signal that comes from the nucleus of the atoms, and they can, you can get a three-dimensional image of anything in the body. Anybody ever had an MRI? Okay, you've had it, right? You get to see your MRI images. They're pretty neat. I remember going over to the magnet lab, and they were doing high-resolution NMR, and they had an orange in there. And so this was just a regular orange, but they could slice it, and you could see where the seeds were in the orange, and you could see all the details of the, of the little cells, of the pulp and everything in the orange and stuff. I mean, it's just pretty amazing, and it's completely non-destructive. You're just sitting there listening to radio waves. You actually hear this kind of clang as the MRI is going on. That's not what bothered me. What bothered me was the confined space for 45 minutes. It took me a day. It took me 24 hours to get over that emotionally. Anyway, of course, X-rays, most of these things, gamma rays, we actually use radioisotope sources, iridium 192, cobalt 60. They're using gamma rays from nuclear decay. We also use high voltage X-ray generators to penetrate steel and aluminum and things like that. If I looked at a mechanical energy spectrum, you can kind of look at mechanical energy in terms of frequency. This is also on frequency, potentially. I just didn't put the numbers in. But if I go mechanical energy, 10 to the minus 2, 10 squared, 10 to the 6, 10 to the 10th, 10 to the 14th, whoops. Turns out, mechanical energy spectrum stops right here, about somewhere around 10 to the 13th. You cannot get a higher frequency than 10 to the 13th with atoms as we know it, because they just don't get any closer together. And we did this calculation once before. If you take 10 to the minus 10 meters, which is the separation between two atoms, and you look at the velocity of sound, which is 2,000 meters per second maybe in some material, and you divide 2,000 by 10 to the minus 10, which is I'm just taking the frequency times the wavelength equals the velocity. So if this is 2,000, and this is 10 to the minus 10, then lambda's got to be 2 times 10 to the minus 10, 2 times 10 to the 13th, right? So that's the fastest that atoms can interact with each other, is 10 to the 13th times per second. Now that's faster than I can snap my fingers, so that's pretty fast, but there is a limit to mechanical energy, how fast I can measure something in there. Where in principle, in electromagnetic spectrum, I'm only limited by the energy I've got to generate those photons. But in here, I have mechanical vibration. I go do a non-destructive test every now and then in my basement. On my boiler, I have an expansion tank. And the bottom of the expansion tank's got water in it, it's got a bladder inside, and it's got air on the other side of this tank. And I don't want the bladder to break because it happened to me once, and my whole system went hydraulic, and I lost a $1,000 hot water heater. It cost me $1,000 to replace the hot water heater. So now every now and then I go and I thunk the container low and high, and it should have a different sound from that mechanical vibration, right? One's full of gas and one's full of water. If I had thunked that when the bladder had failed and it was full of water, I might have saved myself $1,000. Okay, so now every few months I go down there and thunk it. That's my non-destructive test to see if the bladder is still working. Acoustic emission. Pardon me? What? What were you saying? What? It's a very scientific test. Yeah. Well, thumping is a scientific term. Here, if you call it a scientific term, it is. You know, it may sound, I'm kind of making fun of it as we go, but it turns out that when people are refilling oxygen tanks, oxygen cylinders, one of the things they're supposed to do is thunk it. Okay, they hit it. Actually, they hit it with a little hammer to make sure it rings the right way. To make sure that if it has a liquid in the bottom, the liquid will absorb the sound waves and it won't get this nice continuous ring because you'll have a damping from the liquid in the bottom. So they're just checking to try to make sure there's no foreign materials in there. That someone, when they send the cylinder back, it's one of the standard tests is just hit it with a little hammer and listen to it. Okay, sounds pretty crude, but it usually works. So acoustic emission is I take something, I strain it, and then I put a transducer on it to listen to see if it makes any noise at fairly high frequencies, above my ear usually, you know, I mean 100 kilohertz or something. If the thing's under stress, a lot of times it will sort of cry out to you. You can't hear it. Maybe the dog can hear it, I don't know, at higher frequencies. But people use acoustic emission. You just put a stress on it and then you see if the material, if it has a flaw and that crack is starting to slowly grow, it will essentially put little stress waves through as the crack grows. Ultrasonics. Ultrasonic testing is in here where you use a transducer typically at a million, anywhere from 1 million to 10 to the 8th hertz. Most of them at 1,000,000 hertz, you're typically looking at flaws 2 or 3 millimeters in size. Well, 3 millimeters is 1/8 of an inch, right? You can't really get smaller at 1,000,000 hertz. A typical frequency, most ultrasonic machines will have 2.25, I don't know why they came up with that, and 10 megahertz that you can test. You get more attenuation at the higher frequencies, so your signal to noise ratio goes down, but the size of the flaw that you can detect is smaller. If they go to acoustic microscopes at 10 to the 8th, and you now can go in and actually put a semiconductor chip in a liquid bath and vibrate it 100 million times a second, and you actually can come up with microscope images, all the way 3D images that you can slice through this thing without ever cutting it up and actually see if there are flaws there. And there you can get down to resolutions on the order of a few thousandths of an inch. Okay, so there's that. Other type of mechanical testing is proof load testing. Proof load test is basically based on the idea that for statically loaded structures, like let's say a small pressure vessel, a gas cylinder or something, if I pressurize it to 50% greater than the stress it's ever going to see in service, and it doesn't blow up on me, then I can now stress it at 2/3 of that value, or 100% of its design stress, and I can expect that it will probably survive. It doesn't have any flaws that are going to be critical at 150% of the stress, so at 100% of the stress it shouldn't fail either, right? In fact, in flaw size, that's like a factor of 2 because of the square root dependence of the flaw size. So, proof load testing. Now, there's sometimes confusion between design verification testing and proof load testing. Design verification testing, I actually build a structure, I load it up to 125% or 150%, and it doesn't fail, and I say, that's a good design. It didn't fail under the loads I expected it to see in service. I've had people get confused and say, well, that test proves that all the other 100 I built are good. No, it doesn't, because it didn't test for the flaws in the other 100. It just means that the one that I built, whatever this flaw population was sufficient that it didn't fail at 150%. But I could have one out there that has a flaw that's 3 times as big and is going to fail at 88%, and therefore it's no good. So proof load test means you have to test every one, okay, to be sure. So there's lots of different types of tests, and let's see if there's anything else that we have any time to go through. If you want to know more about non-destructive testing, you'll probably have to read one of the books. However, there are all kinds of standards, because one of the problems with non-destructive testing, or certainly non-destructive evaluation, is there's a certain subjectivity or judgmental in evaluating things. There are all kinds of standards. This is a little ASTM standard for American Society for Testing Materials for liquid penetrant inspection. We talked about liquid penetrant, the dye penetrant things. This is reference radiographs for aluminum fusion welds. And so they're actually real x-rays from real standards. And I can call out a particular level of defect that is shown up in these images. Now the problem is this little handy-dandy book has probably cost $700. Okay, and there's about a dozen of them out there. So you can literally spend $5,000 or $10,000 just by owning a set of the standards. So this is a standard you can call out. It's sort of subjective. There is no standard for absolutely pure aluminum castings that have no flaws. Aluminum castings will always have some small porosity. In fact, the tightest spec you'll have in here has some very fine porosity, but it's only 10 or 20 thousandths of an inch. And that's not usually big enough in a metal. It would be in a ceramic, but in a metal it's not big enough. Did I do the calculation down here? Yeah. In a metal, who cares if I got a 10 or 20 thousandths inch flaw? Critical flaw size is much bigger. In a ceramic, I do care about that. So there are standards you can call out, but you have to have someone who knows enough about the design and a little bit of fracture mechanics to be able to determine what is acceptable and what's not acceptable. And that gets us right back to this whole question here of the evaluation of what's good and what's bad. What's acceptable and what's rejectable. A lot of time spent arguing between engineers particularly the buyer and the seller over. The seller, of course, says, well, that's not a flaw. That flaw is not significant. That you can live with that. And the buyer is saying, no, I wanted something better than that. Okay? And the question is, who's right? Well, there's a continuous spectrum in here. And it's probably one of the biggest things, one of the biggest problems is you probably spend, in the cost of a product, you might spend 20% on the non-destructive evaluation. 10% of that might be the testing. The other 10% is just the people arguing. Okay? So that's just the way it is, but it gives me a job, so thankful for it. Thanks. Okay? You can turn it off. If you got